Sorry, I forgot to record. So if anybody has a solution, please tell me. Remember, the solutions to the Diophantine equations have to be integers. So it's been about a minute. So there actually is not a solution to this equation. So 4 and 14 are both even. So 4x is equal to 3 plus 14y. We subtract the 14y to both sides, and we have 4x minus 14y is equal to 3. But we know x and y are both integers, so 4x minus 14y is even. So then, but 3 isn't even, so there's actually no solution.
Trick.
Yeah. So how you make sure there is a solution is that you see the numbers 4 and 14 here. You find the greatest common factor, and you see if 3 is a multiple of that. So the greatest common factor between 4 and 14 is 2, but 3 is not a multiple of 2, so there is no solution. Next slide. So now we're going to go on to multiple equations and only one variable. So I'll let you guys think about this for a second if you find a solution. So it's x is equivalent to 5 mod 7, and x is equivalent to 10 mod 13. So I don't think anybody has come up with a solution, and it is pretty big here, so it's kind of difficult to see a solution immediately. So what we could do is this. So first we rewrite these equations into this as x equals 7n plus 5, and this equation as x equals 13n plus 10. Where m and n are integers, not necessarily distinct or different. So what we could do is, now we know 7m plus 5 is equal to 13n plus 10. Subtract a 5 from both sides. We get 7m is equal to 13n plus 5. Then 13n plus 5 is equivalent to 0 mod 7. But 13 is equal to 14 minus 1. And 14 is a multiple of 7, so we can just remove that. So then we'll have negative 1n, which is negative, then plus 5 is equivalent to 0 mod 7. And this is the same thing as n is equivalent to 5 mod 7. Then we can write n as 7k plus 5, where k is any integer. And then we can plug this back into the equation here, and we'll get x is equal to 91k plus 75. So example could be if k is 0, then x would be 75. The general solution would then be x is equivalent to 75 mod 91. Now, just a fact I want to point out here, this 91 here is equal to 7 times 13. So usually the solution to equations of this type will, when you're given 7 and 13, it's usually their product, but it's actually their least common multiple. So yeah. Next slide. So here is the second example, where this time we have 3 equations. So if a positive integer x, which is greater than 1, is divided by 3, 4, and 5, the remainder is all 1. What's the smallest possible value of x? So I'll write these up in kind of text form. So here we're saying x is equal to equivalent to 1 mod 3. X is equivalent to 1 mod 4. And x is equivalent to 1 mod 5. So what do you think is the smallest possible solution here? So I see Aiden and Roy both have an answer. I'll call on Roy's. So could you explain how you got the answer of 61?
Sure. So if it always divides by 3, 4, 5 and you get 1, that means the number has to be like the least common multiple of 3, 4, and 5. And if you do like the SLAD method, you see that there's no number that is a factor except for 1. So you just multiply all of these together and you get 60. And since the remainder is all 1, you just add 1, so it's 61.
Okay, that's very good. So just to make this a bit more clear, you already explained it very well. So we can so we write this problem as these. So just to make it a tiny bit simpler, you could write you could let y equal to x minus 1. Then y is a multiple of 3, 4, and 5. So y is the multiple of, as Roy said, 60, which is 3 times 4 times 5. Then you add the 1 and be 61. So yeah. So when you see equations where the mods are the numbers are these numbers are different, but these are the same, you can just combine them and you'll and that works. So next slide. Now for the Chinese remainder theorem. So this is just a more general and usually quicker way to solve these. It's not necessarily quicker like for smaller numbers like the examples we had. It's usually easier to just try. But for larger examples like the one we have here, it's usually faster to use the Chinese remainder theorem. So the problem, I changed the numbers a bit, but the problem basically asks, like, there's an army of soldiers, and when they're put into groups of 5, there's 3 left over. When put into groups of 13, there's 7 left over, and when put into groups of 24, there's 10 left over. The numbers are slightly different, so this picture here is like a picture of like a very old document. It's scanned, so does not look like what it actually is. So now, given these, what is n? So here we're just trying to find a general solution for n. A smallest possible value also works. So we see that if we just try to solve for this manually by trying, it's gonna take way too long. So what's a faster way to do this? Well, so first we can write these as some modular equations. So solution like this. So we can write this equation in the form of this. So before it was, I think mod 5, it's equal to 3 here. Mod 13 is equal to 7, and mod 24 is equal to 10. Now notice that in this example, this part and this part are both, this part and this part are both multiples of 5. So when to modular 5, only this part is left over. So then we just have to find an A2 that satisfies this is equivalent to 3 modular 5. And you see the same thing with 13 and 24. So you see there's a 13 here and there's a 13 here. So then this just has to be equivalent to modular, this has just to be equivalent to I think 7 modular 13. So you can separate this one big equation into 3 smaller equations that we know how to solve. So these are 3 smaller equations. So one solution is A1 is equal to 2, A2 is equal to 4, and A3 is equal to 11. And then we plug this back into the equation above here. And then we'll get that x is equal to 2,698. Remember, this is only one possible solution. So then the general solution would be this. So let's say you had 2 equations. So you could do the same thing, except let's say you had, I don't know, something like x is equivalent to 6 mod 8, and the x is equivalent to 3 mod 13. Then we could let x equal to 6 times a, then plus wait, no, not 6, sorry, 8 times a, then plus 13b. And then we would just have to find AA such that 8A is equivalent to 3 mod 13, and 13b is equivalent to 6 mod 8. So that's what you do if you had like a different number of equations instead of 3. So the next slide is 2 variables and 1 linear equation. So this is a different type of Diophantine equation. So let's say the equation was 731x plus 578y is equal to 51. Now, this might seem very big, so how do you suppose we solve this? So I'll give you guys a moment to think about this. And if you have an answer, you can type in the chat. So the numbers are very big here. So I doubt we can just find a solution by looking at it and trying. So how we solve this is we have to use the extended Euclidean algorithm. But first of all, what is the Euclidean algorithm? So it's an efficient method. So it's a way to find the GCD or GCF of 2 integers. So let's start with an example of 1001 and 294. So we start from the smaller number, 294, and we do mod. So we get 1001 is equivalent to 119 mod 294. Do the same thing with, but now we take this 294 and 119 instead as the 2 numbers. So then we get 56 and 119. Now we do this again, and we get 7 and 56 instead here. And we just keep doing this until we get to 0. Then the smallest number you see that isn't 0 is the greatest common divisor of these 2 integers. So here it would be 7. And if you check that in the calculator, it is 7. So then, next we're going to talk about Bezo's identity. So the theorem, which is called Bezo's identity, is that so first we have 2 integers, a and b, and we call their greatest common divisor as d. Then there exist integers x and y. They can be negative, such that ax plus by is equal to d, which is the GCD of a and b. So the proof of this identity. So first we use Euclidean algorithm on a and b, and we get these steps here. And there's usually some steps in the middle. So we can notice that R1 is equal to a minus x1b. So sorry. R2 is equal to B minus X2 then times A minus X1B, which is equal to a bunch of A's and B's added together. And we can express R2, R3, R4 all the way down to Rn, and then also D using A and B. So eventually then we can express D as something A plus minus or plus something B, which equals D. And that completes the proof. So how do we find this X and Y? So like the problem here, how do we find the X here and the Y here? So what we would do actually, it's just we can follow the steps listed in the proof here. So let's use 1001x plus 294y equals 7. So first we see these were the steps of the Euclidean algorithm that we had. So then we first express 119 as this. Then we express 56 as 294 minus 2 times 119, and so on. So you can keep going down until we get that 7 is equal to 5 times 1001 minus 17 times 294. So this gives us one solution for this Diophantine equation here. The general solution is of the form x equals 5 plus, so here next to x we have 1001, so it's 294, the other number, then divided by the greatest common denominator, which in this case is 7, which this is 5 plus 42, and then for the other one it's the other number over the greatest common denominator. So for y, we get negative 17 minus negative 143 in. Let me clear my drawing. So remember that going through all this Euclidean algorithm and Bezo's identity was to solve the Diophantine equation 731x plus 578y equal to 51. So how might we solve this? So we use the Euclidean algorithm and find that their GCD is equal to 17. Then you have to notice that 51, this is equal to 17 times 3. So if we just multiply 3 to this A and this B, we'll have a solution for the equation, for this equation. So I won't go through the extended Euclidean algorithm to find x and y themselves, but yeah, that's how you would solve something like that. Now let's change the equation up a bit. Instead of 51 here, what if it was equal to 27? Would there be a solution? So there would not be, because 731 and 578 are both multiples of 17. So this part has to be a multiple of 17 as well. However, 27 is not a multiple of 17, so there's no solution. Now next we're going to talk about modular inverses. So modular inverse of an integer a with respect to the modulus m, this number here, is an integer x such that ax is equivalent to 1 mod n. So a is a given number. So we've seen problems like this solving a linear Diophantine equation. So you can solve this using Bezo's identity. So how you would do this is, first you would rewrite ax is equivalent to 1 mod m as ax is equal to 1 then plus mn. So these are both integers. Then we subtract the mn from both sides to get ax minus mn is equal to 1. Now for this to be true, so we know that M is given and A is given. So by Bezo's identity, so first we have to know that A and M have a GCD of 1. So then by Bezo's identity, there exists an X and an N such that this is equal to 1. So you can use the extended Euclidean algorithm to eventually find X. So we could do an example here. Let's say we have 4x is equivalent to 1 mod 7. So then this would be the same thing as 4x minus 7n is equal to 1. We can use the Euclidean algorithm here and find that x is equal to 2. So then we could plug it back into check, and indeed 8 is equivalent to 1 mod 7. So next is the Fermat's-Little theorem. So if p is a prime and p does not divide the integer a, then a to the p minus 1 is equivalent to 1 mod p. So we won't go over the proof of this because it's fairly complicated. We don't have enough time for that. So example could be 2 to the 6th, which is 7 minus 1, is equivalent to 1 mod 7. So if we check this, 2 to the 6th, by some memorization, I know is 64. And 64, we know is 63 plus 1. Now 63 is a multiple of 7. So this would be equivalent to 1 modular 7. So there's a more general version of Fermat's-Little theorem, and it looks very similar to this, except it's the power here is slightly different. So let's say I'll define what this phi n is later. So after I finish this, so this phi n is numbers that are the amount of numbers smaller than n that don't share a common factor. So let's say n was equal to 6. So 1 would not share a common factor with 6. 2 does, 3 does, 4 does, and 5 doesn't. So then that would be, so there's 2 numbers here. So then a squared must equivalent 1 modular 6. But then, as the same rule, it's that a and n cannot share any factors. So you can try this for, let's say, some number like 5. 25 is indeed equivalent to 1 mod 6. And the proof of this is also very complicated, so we don't have enough time to go over that. So that's it for the lecture today on Diophantine equations. So there's also an application here, but we're running out of time, so yeah, we won't have time to do that. So yeah, that's it for the class today. See you guys in 5 minutes for the solving the problem set. Sorry. Okay, so I'll end the meeting and see you guys in 5 minutes.
Bye. We have literally less than a minute.